So let's get started. Welcome everyone. Thank you for joining the RISE EC Computer Engineering Distinguished Speaker webinar today. Meanwhile, I will monitor the Q&A chat during the talk in case there are questions that make more sense to be addressed or clarified in the middle of the talk. So next, it's my great pleasure to introduce today's distinguished speaker, Professor Boris Marman, who is a professor of electrical engineering at Stanford, where he is also the founding faculty co-director of the Stanford System X Alliance and the faculty director of Stanford's System Prototyping Facility. So he joined Stanford after completing his PhD at UC Berkeley in 2003. From 1994 to 1997, he was with Neutron Microelectronics, Germany, where he developed low power and smart power ASICs in automotive CMOS technology. So Professor Murmann is a world-renowned researcher in mixed signal integrated circuit design, with the emphasis on sensor interfaces, data converters, and custom circuits for embedded machine learning. So he has worked as a consultant with numerous Silicon Valley companies and also received many awards and recognition, including the following: Best Paper Awards from both VLSI and CICC, both of which are top-tier conference for integrated circuit design, the Angelan Early Career Professor Award, and the Rick Wilhelm Bassett Research Award. And he has served as an associate editor of the IEEE Journal of Solid-State Circuits, an ADCOM member and distinguished lecturer of IEEE Solid-State Circuit Society, as well as data converter subcommittee chair and the technical program chair of the IEEE International Solid-State Circuit Conference, ISSCC. Many of you know this is the best conference for integrated circuit designs. Also, he is a fellow of the IEEE. And finally, he has the community recognition that all researchers would dream of. So anyone who works in his field, meaning mixed signal integrated circuit design, has read and is familiar with his work. So thank you very much, Boris, for accepting our invitation, and the rest is yours.
Thank you. Thank you very much, Yingyan. Thanks for this very generous introduction. It puts a lot of pressure on me here to deliver something good for this audience. Thank you all for attending. I know these are very tough times, and hopefully we can have some fun together this afternoon, and in fact have some discussions after my presentation. I want to talk about topics that are fun for me these days, and of course, as a mixed signal circuit designer, this has a circuits context, but we will actually venture a little bit more into the system and algorithm land, so you will not see too many schematic diagrams in my talk. So let's look at a typical mixed signal interface from a bird's eye view. Everybody has seen this. This is a paradigm that is over 100 years old. We take analog signals, we amplify them, we filter them, we do data conversion, digital processing, and then perhaps we send it off to some other location. So these interfaces have been in the making for many, many decades. However, what's interesting is that emerging applications still continue to push the limits on these in terms of power dissipation, integration density, and input dimensionality. And this is essentially what motivates this talk. Where does this lead us in today's world? So I want to make this more colorful with a few examples. Here's one from my colleague Amin Arbabian at Stanford. This is on ingestibles. And so in ingestibles, you basically try to build miniature instruments. And in this case, they actually built almost an entire ultrasound machine in the form factor of a capsule that you can swallow and do some imaging in your GI tract. And so obviously this pushes all the various blocks and functions to the physical limits, and it's quite remarkable what can be achieved within these form factors. Another very exciting and futuristic direction is brain-machine interfaces, where we try to get tens, if not hundreds of thousands or millions of electrodes to connect to brain tissue or other types of tissues to do massively parallel recording and analytics on neural signals. So here you see some snapshots from Neuralink, which is one of Elon Musk's startups. And so this really pushes the envelope in terms of data rates, and it is extremely sensitive to power dissipation, because these circuits will either be implanted or be very close to your brain and skin and so on. So they're not allowed to get very hot. So the bad news is, right, so while there's all this excitement about new applications and so on the technology side, we're actually approaching some limits. And so this is my slide on Adc energy efficiency. On the y-axis, it's leveraging a figure of merit that basically tells you how energy efficient the data converter is. On the x-axis is time. And there are many points here. And the interesting thing is that the progress, since I've been tracking this for about 20 years or more, is about 1 dB improvement per year. So this doesn't sound very impressive. It's doubling every 3 years. But when you do this for 20+ years, good things happen. And the unfortunate thing, though, is that we're reaching levels of efficiency that's starting to challenge some of the physical constants. So at some point, thermally imposed limits on how much energy is needed to digitize is going to near. And this is when we will run out of improvements. And so this is, of course, troubling, given that we want to squeeze out more and more and more of these interfaces. Let's look at another angle, kind of the back end of these systems. Nowadays, we want to achieve data analytics and learning in an increasing number of systems. You see on the left, any kind of gadget is collecting multidimensional signals that are unstructured in some way, and you want to infer useful information. So the new way of doing this is to try to do much of the computing on device to improve privacy, latency, and to avoid data communication to the server, which is extremely expensive. The challenge is that these algorithms tend to require billions of operations. And how do you squeeze that into this form factor and maintain good battery life? So we've made a lot of progress on this front, but one of the unfortunate boundary conditions is, again, that there are limits inside in terms of the raw underlying technology basis. And so here's a plot that simply has normalized logic energy. The energy it takes to switch a logic gate on the y-axis. On the x-axis is the technology node. You could also think about this as time. And so while you see that kind of in the previous decade, when we went across 4 technology generations, the power or the energy of digital logic has come down perhaps by an order of magnitude. And most recently, in the same time span, it's more like a factor of 2. So all of these improvements in terms of raw efficiency of building blocks tend to be diminishing these days. And this has implications on how we're going to do system design in the future. So this is kind of the motivation for the topics that I will present. And the main argument I have is that future gains in these systems must increasingly come from customization to specific applications and domain-specific architectures. This is in fact already happening in digital circuits. You know that domain-specific architectures is a very big topic in digital design. But I foresee this is also the paradigm going forward for mixed signal systems. And specifically, the opportunity lies in blurring the boundaries between what is actually analog and digital and how does it communicate. So no one should think just analog or digital. We should think information. We should think what is the best way to acquire and handle and transmit the data, regardless of what its representation is. So none of these are new ideas, but I think they have become more relevant than ever. And I foresee that this goes from academia into industrial practice at some point, because it's the only thing that's really left to improve efficiency. So now, going from this very abstract argument, I want to make this more colorful and do a couple of deep dives of ongoing projects within my group that are basically running on these principles. We want to innovate by coupling the design of the mixed signal circuits more strongly to the application and its underlying needs. The first one is an artificial retina, and the second one is a machine learning processor application. And so I will go into these in more detail. So let's start with the retina. So the high-level motivation here is that there is a need to cure age-related blindness. So you may be aware of this. As people age, there are various diseases that will make you lose photoreception in your eyes. So these diseases are called macular degeneration and retinitis pigmentosa. And the question is, can we do something on the technology front to restore sight in these types of patients? So this is not a new topic, but there's a lot of new energy in it. And the main idea behind every project related to this subject is that you basically recognize that, yes, while the photoreceptors that do the optoelectrical conversion in the eye may have died, the retinal ganglion cells that are actually communicating the information to the brain are actually often still alive. And so you may be able to build an artificial system where you have a camera that takes the image, a processor that figures out how to stimulate, and then electrodes that connect to these retinal ganglion cells to basically create a virtual image in your head in absence of functional photoreceptors. Now, this problem is tough because you need a lot of electrodes, ideally more than 100,000, to have a high fidelity image. And the pitch is very dense, perhaps on the order of 30 microns. So the system that we are working currently looks like this. So when you have a cross section of the eye, you will definitely need to have a chip in the eye that stimulates these electrodes. But you cannot have all the electronics in the eye, because that would essentially destroy the tissue with its power dissipation. So within the eye, you're limited to about 10 milliwatts. The rest, whatever is outside, can be more power intensive, for example, these cameras, and there will be wireless power transfer and so on. So many people and companies have worked on this, but what sets our effort apart is that we're trying to really figure out how the eye actually works and what is required to stimulate the retinal ganglion cells properly to achieve a very high fidelity artificial image. So I am, of course, not an expert in that area, so I'm teaming with people. My collaborator is Professor E.J. Chichilniski at Stanford, and he writes very nice papers, and one of them is, I think, called "The Eye is Not a CMOS Imager." This appears, at least in his talks, very frequently, and that is to say that you cannot simply stimulate these retinal ganglion cells based on whatever patch is bright or dark. It doesn't work like this, and this is because the eye or the retina has many different cells. Some actually react to bright light, some react to dark, some have different firing rates than others. So it actually matters which cell is where and how you stimulate them. The other issue is that the retinal ganglion cells, they basically lie in this very dense wire harness, which are the axon bundles. And so when you put an electrode array on top of this, which are these red dots, you have to be careful that you do not stimulate the wires, because that leads to a completely wrong perception. You want to figure out which electrodes are actually connected to a ganglion cells, and the others you may want to avoid. So to learn about how to do all this, my collaborator has done a lot of research in the last 10 years. And as crazy as it sounds, he actually takes live retinal tissue from animals. He puts this on a setup in a lab, and then he literally shows these tissue slices video images, then he detects the firings on the opposite end to figure out what the eye tells the brain literally. In other words, what is the transfer function from video to electrical activity in the retinal ganglion cells. And so this has created now a wealth of knowledge on how this should exactly be done to create a nice image. And it has inspired the design of our current system. So let me dissect this into its different parts. So on the left is what we already discussed. This is this electrode array that we're going to stick into the eye and hopefully hit some of the meaningful retinal ganglion cells while avoiding stimulation of the axons. What do we need to do this well? Well, we basically need to do a couple of things. The first one is we want to figure out which cell is where. And it turns out this can be done by just looking at spontaneous neural activity. So these cells, they're constantly firing regardless of what is going on in their environment. And from the shape and the characteristics of their spiking, you can actually figure out which cell is what. And so from here, the first step is to figure out what are the available neurons and which ones are associated with which electrode. Now, once we know that, we can start stimulating them. This is the second step, and then we can see how they respond. And from this, we can learn how the different electrodes actually act upon each of these cells. And once we have this, once we've gone through these two steps, which is a calibration step that the individual may do at night or once a week, or some of this may be happening while they're sleeping, we build up a dictionary, and this dictionary really informs then how the camera image is translated into stimulation in the eye. So there are thousands of challenges in making this work, and I just want to talk about the first one, which seems to be easy, but it's actually extremely hard, and that is the first step, this recording. How do you record from tens of thousands of electrodes simultaneously in the eye at a very small power budget? So the issue is the following. If you looked at each one of these electrodes, their neural signals, they're not extremely wideband, but they still need to be sampled at about 20 kilosamples per second to retain the spike feature. So that's the Nyquist rate. So if you add this up, 100,000 times 20 kilosamples per second, that's 2 gigasamples per second. If you multiply that with, say, 8-bit resolution per sample, you end up with a data rate of 16 gigabits per second. So this is kind of what the data connection to my university building handles. It's not something that you would easily, bring in and out of the eye. And so this is literally like drinking from a fire hose. So this is what this cartoon wants to say here. So can we somehow skip channels? Can we do sort of some dirty tricks? Well, a lot of things that are in the literature right now don't really work, because we cannot just threshold spikes and merely detect their presence. We actually need the spike shape to figure out which cell is where. We also want to look at all or most channels simultaneously to see spatial progression, so that we can figure out where are the wires, where are the axon bundles. That tells us actually which areas to avoid. So we need very dense spatial and temporal information. However, one area of attack is essentially the signal portion outside the spike region. So what mostly matters in terms of information content is when these when these spikes fire, when these cells fire as a spike, and what the shape of that spike is. What doesn't matter so much is what the baseline is and what the noise around the baseline is, as I'm showing here. So when you look at this, a neural signal has a duty cycle, depending on its activity, somewhere between 1% and 2% or so. So there's actually a opportunity to throw away about 50 to 100x, or to get 50 to 100x compression by throwing away the meaningless samples. So that leaves us with the problem now, well, how do we do this? If we first acquire and digitize these samples, that would be very hard to handle. And so let me talk about this in the next couple of slides. So suppose I just did a raw digitization of all this data. My ADC running at 2 gigasample per second. If I run the number and if I do a very good design, that gives me maybe about 1 picojoule per sample energy. The ADC itself would actually be just 2 milliwatts. That doesn't sound too bad. I could actually still do this as a good analog designer. But the problem really lies in getting the data out. So if I have an optimistic wireless transmitter that is perhaps 10 picojoules per bit, that would already be 160 milliwatts, about 16x over my budget. So what this means is I need to somehow compress the signal, as I just suggested. Now, if I did this digitally, I actually also wouldn't be able to complete this system, because sending 16 gigabits per second into a digital compressor that analyzes these and looks at them one by one and writes some of that to memory, right? Because if you have 16 gigabits per second coming at you, you definitely need some caching and so on. This is very, very difficult to do, and in fact would also exhaust our power budget very, very quickly. So the solution that we came up with is to do something entirely different and something that's a little bit unconventional. We tried to implement data compression during A to D conversion, and we're using the signal properties to achieve this. Namely, we're using the fact that we're only interested in the spikes and the exact shape of the spikes, but not much else. So let me explain to you one by one how we do this. So whoever is not an ADC expert or mixed signal expert, bear with me for a couple of minutes. This goes into a few details that may be a little bit hard to understand, but I know many people will follow. So first, let's look at how we do the digitization. So we acquire samples. So we take these samples, these blue points represent samples in time. Then we need to figure out what is the sampled amplitude. And the way we do this is using a concept called ramp or single slope A to D conversion, which is actually relatively simple conceptually. You run a ramp against the sampled signals, and then you find the trip point in time. You figure out when does this ramp cross the sampled signal, and you have a counter running that accounts for this time. So you essentially perform a conversion from the voltage to a pulse position. So it's like a pulse position modulation of the signal. Now you can imagine if we have many of these, let's say I have many of them running in parallel, let's just do 4. I can run these ramps together and I can figure out when does each one cross, and these pulse positions tell me for each channel, what was the sample that I took, which digital value does it correspond. So the interesting thing that we do now with this information is that we create an array where these events compete with one another in a wired OR fashion. So instead of building a readout where each one of these slope converters, which has a comparator as shown here, gets a path to the output side of the array, we just build an XY wire grid, and we let each pixel pull down these wires whenever the comparator fires. So in other words, we make these A to D converters, these individual A to D converters, compete for the finite resources in this array, which is basically, if you think about it, we have n square of these converters, but there's only 2n wires, and they somehow have to compete for these. So what does this do? What does this competition do? So let's look at it. So if I use an example of just one pixel firing, and I just use an example of 4 here. If this pixel fires at a unique time when no one else is firing, I can triangulate this information out of the array, and I can say, oh, at time t equals 5, this pixel crossed the threshold. This means the sampled value of this pixel was 5. And I can determine that without any ambiguity. That would be very nice. I would get the information out that I want. However, there's definitely this possibility, because of the competition across the wires, that another channel happens to hold exactly the same sampled value, and hence these two events collide, and they try to pull down exactly the same wires. And so now this creates ambiguity in this array, and so we call this a collision. So same sample value at 2 locations. It introduces ambiguity due to the wired OR. So what do we do with this? We decided to say, let's just throw this away. We say, well, too bad, this information, we just lost it. And in fact, this is what leads to compression. And what I want to show you now is essentially explain to you why this compression is actually very, very elegant, and it applies perfectly to this type of signal. So when you think about how these signals are structured, the probability that 2 samples are exactly the same is the highest near the baseline, because these signals, they hover around the baseline for a long time, but they're only outside of the baseline for a very short time. So the probability that these blue samples are unique in time and amplitude is actually very high. So in other words, the probability that they get eliminated by this wired OR competition is very low. And so what happens in this scheme then is that this very brute force kind of during A to D conversion compression removes mostly the unwanted sample and keeps most of the blue samples that we like in a very native way. So it's sort of a self-elimination of useless samples during the A to D conversion. So we wrote up a journal paper about this. There's a lot of details. You can use multiple wires, and there's all sorts of tricks you can do. But here's just a snapshot of what the signals look like that come out of an array like this. So instead of getting a very detailed Nyquist waveform that has all these wiggles and noisy artifacts, we get primarily just the samples that are unique, that represent the spike. And the rest of it gets mapped into straight lines and very simple patterns like this. And this reconstruction is an art by itself, but this gives you a feel. So this gives us about 40 to 100x compression depending on what the signal looks like. And when we test this for the fidelity of how many cells can we still recognize properly, because this is the ultimate specification of this piece of the system, it's actually most of them. We get 90 to 95% of all cells identified correctly. And this 5% loss is not extremely critical, because we tend to lose half of the cells already because they are masked by axons and so on. So within this system, this is actually a completely tolerable loss. So this research is ongoing, and we have taped out a chip. That chip is being tested right now. You can imagine that testing something like this in vivo is not easy. And so that's what we're still working on. This chip is actually functional electrically. Here you see this big array. Well, it's not super big. It's a small start. We're just having 1,000 inputs here. Ultimately, this would be 10,000 or more. And we're going to package this with a microwire bundle to get all these channels out. And then they will connect to some retina tissue, and this will be evaluated within the application. So this is extremely exciting to me, because this application made it possible for me to innovate in a direction that is otherwise not possible, because it's just so closely coupled to the signals and their properties. So let me now shift gear and let's go to the second topic. Everybody's talking about machine learning nowadays. Obviously, this is the latest thing in town. Everybody is excited about it. There's a real wave going on. And these two figures probably capture most of what the hype is about. The left diagram is from my colleague Andrew Ng, who as early as 2012 drew diagrams like this, recognizing that this new form of machine learning, which is called deep learning, seems to get better and better and better the more data you put into it. And it actually outperforms any other known algorithms with vast amounts of data available. The other characteristic picture is that if the CEO of a hardware company says data is the new oil, that really means we've entered a completely different decade of innovation. And so again, what's driving much of this is the explosion in data. This is a nice chart that essentially shows, I always find it mind-boggling when I look at this. When you plot it on a linear scale, it almost looks like we didn't have any data in 2008 or 9, and really all these mobile devices and data centers and linking everything together has really led to an explosion that on one hand creates a lot of data that can fuel new algorithms and the training of new algorithms. On the other hand, it creates a lot of unstructured data that we want to make sense of. And it turns out a lot of these come from your sensors, from your daily sensors and so on, as I indicated at the beginning of the talk. So there are many algorithms now for figuring out how to make sense of this data, but by far the one that receives quite a bit of attention nowadays is the deep convolutional neural network, or CNN. Many of you may have seen this. It's a very interesting algorithm that runs essentially correlation across input images. So you have filters that run across these images. They look for edges, for example, in the first few layers. And then they create increasingly abstract representations of these informations. In the beginning, it may be edges and simple gradients. Later, it becomes more complicated features until you get to pretty high-level features that allow you to make decisions on whether you're seeing a car or whether you have a red light or something like this. So this has proven very effective, in fact, unreasonably effective, as some people call it. But this is really something that everyone is trying to leverage now. So what I want to get into a little bit is how to efficiently build these algorithms. One of the challenges is that there's a huge number of computations that needs to be done. So the elementary operation is shown here. It's what they call this three-dimensional convolution operations. So you have an input volume of data. You could think of this, if you have an RGB image, the dimension C would be 3 because you have red, green, blue, and then you have X and Y. And so you would have 3 channels. And then you run a set of filters through that data across the entire image. And these filters, they get dotted with the volume inside the input. And you have many of these. In fact, you have as many of these as you want output channels, and the number of output channels can be blown up in this example to maybe 100 or 200. So you have many of these filters, and every time you perform this huge dot product between these 2 volumes, you get 1 pixel out. And so then you fill this volume, and then you go to the next layer, and you may have 50 layers. So if you multiply all of this out, you can have millions of weights. 10 million weights or so is pretty common nowadays, maybe 5 to 10. And then you have billions of these multiply accumulate operations. And so getting that to work very efficiently has been a topic for many years now. So by far the most common paradigm is to do domain-specific hardware. And so a digital accelerator or a neural processor unit, NPU, is what many people are working on. So this is an example of a domain-specific piece of hardware, because this hardware specializes on doing really well with convolutions and the types of operations that are required in deep neural nets. It would not be very good in running other tasks. I don't know, like running Microsoft Office or something like this. It wouldn't be able to do that actually, but it's kind of customized for this task. One of the key aspects of that type of processor is actually that it heavily exploits data reuse in these computations. If you recall, we have these filters, and these filters, they get loaded from memory perhaps, and then they get moved around a data volume. So you could keep these filters stationary for some time while you do computations, or you could keep partial sums stationary while you shift in and out new weights. So there's a lot of opportunity for temporary caching in these digital architectures. And this is a huge research topic by itself on how to do that optimally. So people have come up with architectures that look typically like this. You have a main piece of memory. Often this is off-chip DRAM. Then you have a global buffer that could be a few hundred kilobytes SRAM. Sometimes it's a double buffer. And then you have this processing element array that basically provides a high degree of parallelism to do multiply and add to carry out these convolutions. And so inside each PE is something like this. You have register files, also for temporary caching and reuse. you have a multiplier and an adder. And so you have many of these. You can have many flavor systolic arrays and so on. So one of the issues that is clear from these architectures, as much as we optimize them, there is still a lot of overhead in data movement and register file and memory access. For example, what often happens in a state-of-the-art accelerator is that while this multiplication is actually relatively cheap, every time you do a multiplication, you may have to access a register file at the input, at the inputs, at the output. And so you tend to drown in this extra energy of just supplying data to your compute elements within the PE, outside the PE, and so on. And so one thing that I got very excited about is how about trying to explore a mixed signal version of this that gives you a degree of freedom that may allow you to build denser arrays that have better amortization in all of these memory accesses. And so we've been looking at this for a while. And here is essentially the first incarnation of it as a cartoon. This is my former student, Danny Bankman's ISC paper from 2018. And the idea is relatively simple and aggressive in some other way, because here we just use 1-bit weights and activations, but I will show you in a moment how we can extend this. But the idea is essentially this. So whenever you have to process an input volume of data, unroll this. So we have fx by fy by c. Unroll this into a linear vector 1 to n, and then broadcast this entire vector across an array. Now, within the columns of this array, you have all the different filters that have to process that very same input data volume. So what happens on the input side is that you amortize this memory access very, very heavily, because you push this data into the array with one memory access, and then many computations happen on that data. The filters themselves, we keep stationary for a long time in these arrays. At some point, they may have to be reloaded because you have to move on to other filters or layers. But we try to keep them stationary in local memory in each cell here. This could be just an SRAM cell or something like this, for as long as possible, so that there's close to no data movement on the weights as well. So the result is that the input memory access is highly amortized and the movement in the weights is minimized. So then we do mixed signal computing, and what it means is that we do the multiplication with an XNOR gate. That's all you need for a 1-bit system. And then we use analog where it's really good at, and that is accumulation. Because adding numbers is most easily done by summing charges or currents on a wire. And this is really where analog shines. There's no digital equivalent for this. If you want to collect some charges, can really be beautifully done in analog. So to give you a feel for the dimensionality, the chip that we built has 1,024 rows and 64 columns. And that fits very easily on a chip and can give you very good throughput. So since this is a binary net, these output A to D converters are just comparators, and at the same time, they're the activation function of the system. Here I highlight again, so when you do one operation with this array, you basically in each column get one pixel out, one output pixel. And then you shift new volumes in and you get the additional pixels until you run out of filters, and then you reload them and you move to the next layer. So we made a complete prototype IC out of this. It's a small network, admittedly, and you see here 2 by 2 by 256. This unrolls into this dimension that I just mentioned to you, 1024. So we have a big array here with these synapses and neurons, if you want to call it that. And then outside of it, you have these filter SRAMs that are feeding this array. And as I said, key is that these accesses to these SRAMs are highly amortized. This is still one of the few mixed signal chip demonstration that actually has image data going in and the final labels are coming out. So what class is this? Is this a dog or a cat, and so on. Many demonstrations just limit themselves to build a small piece of the computing, And then it's actually easy to be very efficient because you're not accounting for a data movement around your computing, but this is actually a very important aspect that you need to handle. So for those who don't know, so this chip does not address a very difficult machine learning problem. It's a CFAR10. Many of you may know this data set. So you basically have to differentiate between these different types of objects. There's 10 different ones, right, between cats and dogs and cars and so on. And humans tend to get these right to about 94% accuracy. And in our system, this is this red circle data point that I have here. We achieved 86% accuracy, and this had mainly to do with the small filter size that we used. We used 2x2 filters, which is not so optimal. It costs you several percent. We could have gone here with 3x3, but it wouldn't fit our chip. We now know better. We could have done this differently, but this is the data point we generated on this chart, which has energy on the y-axis, accuracy on the x-axis. And so there's a few contenders. Design 6 is something that I was also involved in. This is a digital version of it, which is significantly less efficient, maybe a factor of 3 to 5. And then there's Naveen Verma's compute in memory work, which I will talk about in a moment as well, which is also performing really, really well on this data set. These points here are just for comparison, right? If you used more generic digital compute engines like GPUs and MCUs, it would be orders of magnitude worse. And this is not surprising because these are much more flexible architectures. So the energy gains here really come from customization for the deep learning application, and additionally from squeezing in some analog goodness where we could. So when you inspect this chip more closely that we have, the unit elements that we constructed at the time are still actually relatively big and bulky, and definitely we wouldn't do it again like this. So the single bit weight that we store in each synapse is a latch, and a latch is relatively big compared to an SRAM cell, for example. We also used differential signaling, which was probably an overkill. So that brought up the gate count to 2. There's a clear signal that is needed to reset the charges every now and then, and we have some east-west communication to ping pong between 2 pieces of memory. So overall, this can actually be reduced quite a bit, and this has meanwhile been shown by others. So going from this memory-like architecture, as we like to call it, which uses a latch and then some standard CMOS gates, you can build something that is much denser, basically using a 6T SRAM cell, and then maybe you have another 2 to 4 extra transistors that emulate this functionality, this XOR, and you may find other ways to do the charge transfer and charge reset. So this essentially is a huge improvement in the cell density. Also, there have been architectural innovations that allow you to do serial arithmetic to do multi-bit operations with this, so that you're not limited to 1-bit processing, which is actually quite limiting in scope in terms of the architecture. So next, right? So if I want to go further down this trend on where this is going, definitely you could say, well, these SRAM cells are even not that dense. I would like to have something way denser, where I could fit many tens, if not hundreds of megabytes on a chip to store entire neural networks, perhaps in a weight stationary manner. And this is where emerging memory comes in. And so this is a topic that I'm also very interested in, and I'm working on the side. It's just moving a lot more slowly because these technologies are not necessarily readily available. But once they are, it is quite an interesting idea to explore, because you may be another order of magnitude denser than SRAM. And this means you could potentially have much, much less data movement again, and much more parallelism. And within one clock cycle, you could basically perform a lot more operations. There's also the interesting aspect here that these memristor-like cells that you find in emerging memory, like RAM, they can potentially hold multiple bits per cell. So not only is this cell small to begin with, but it also holds multiple bits of information. So the ultimate idea, right, and this is kind of what several people are exploring, can you put a whole neural network on a chip without external memory, where each one of these RM arrays is essentially one neural network layer. It holds millions of weights and it performs computation, again, actually through KCL on these bit lines, and then you have A to D converters at the edge and so on. And you essentially pipeline your entire network through this, and you just have very small buffers, SRAM buffers adjacent to these to hold the current working set as it ripples through the pipeline. So this clearly is, again, a very interesting D2A and A to D problem, and this is obviously why I'm involved. So on the other hand, recognizing that these emerging memories have their own challenges, they're not readily available, the cells are very dense, so making things programmable and reconfigurable is not so easy. You may have arrays that have to obey push rules and so on. Is there another paradigm? And this is something that we have been asking now for a while as well. Is density everything, or could we actually do something in the middle that uses larger multi-bit mixed signal cells that are still significantly smaller than a digital processing element, but larger to do parallel multi-bit operation and to enable some reconfigurability within an array? So here I'm indicating, this is definitely one of the challenges with anything mixed signal or in memory. The kernel sizes, they vary from layer to layer. So maybe sometimes you cannot use the entire array in the X direction, sometimes in the Y direction. And this is when this amortization benefit fades that I've been talking about. If the kernel is larger than the array, you may have to do digital accumulation, and now the ADC spec may become very critical and so on. So figuring this out is actually a very hard problem, and to my understanding, no one has figured this out. How well do such architectures perform? How do they compare with digital? And how should the data flow and schedule look like that utilizes these arrays? So this is where I actually have teamed up with Professor Len, and we are working together and establishing a framework that tries to answer these questions. It's well established for some of the standard digital architectures. For mixed signal, it's not. But it's actually very important for this to become practical that we get the big picture story right and that we do full system level optimization and analysis and design. So here's another aspect that is very important to mention. Earlier on the slide, I had this argument that for neural network inference, it turns out somewhere between 1 to 4 bits. Definitely 4 bits is enough for many inference applications. But could we do 8 bits efficiently with mixed signal? And there I have to say I'm a little bit negative. This is an analysis of this structure that I had on the previous slide that does multi-bit MAC operations with switch capacitors. And the moment you get close to 8 bits, your efficiency is actually not much better than digital. And this is because you have to expend quite a bit of energy to overcome thermal noise in the data converters and then other pieces, and things get larger and so on. So this is a preliminary analysis that I've done on this, and it essentially shows you that if you stay in this regime of 4 to 5 bits, you can have an order of magnitude over digital, at least at the array level. And then you want to make sure that you come up with a data flow that doesn't evaporate these gains. And this is really where the most important work lies now. It's actually not difficult to build a tiny array that is very efficient and you quickly claim success. But how about building a complete processor that contains this? What is the end of the day efficiency of that? And that still needs a lot more work than has been done already. So the verdict of this whole line of research really culminates in this one question: how flexible can we make this mixed signal and in-memory approach to machine learning inference while retaining a significant energy benefit? I think it's very difficult to dispute that fully digital will always be slightly more flexible than whatever you can do with mixed signal and in memory, because a lot of things are pre-allocated in these designs, whereas there are more serial in these neural processors. So as you go from CPUs, which are extremely flexible but extremely inefficient at the same time, to GPUs, which become much more efficient, a little bit less flexible than CPUs, to digital NPUs, which try to strike a good balance, can we get our 5 to 10x from mixed signal and try to push this point as far as possible to the right to actually be competitive with these NPU architectures? So I think the jury is still out on whether anyone needs this. Does anyone like to have this 5 to 10x benefit in return for some loss in flexibility? My opinion is yes. It is really just a matter of maturity of the field. As electronics mature, you tend to value efficiency more than flexibility in many applications. And we've seen this in a lot of different spaces, let it be radios or whatever. And I think in the next 10 years, this may also become true. So this is the end of my talk. I hope you enjoyed these two examples to make sense of my general message, which is basically summarized as follows. I strongly think that there's a lot of room for innovation between the analog and digital domains by thinking about application-specific customization, leveraging the fact or addressing the fact that these interfaces are moving toward higher dimensional signals as we go. This promotes local data analytics, learning, multi-dimensional problems with lots of memory. But at the same time, you have this data-driven nature that allows you to be noisy and somewhat inaccurate. And that basically brings analog on the roadmap as something that can be considered. The building block boundaries, they basically disappear in these schemes. You may sometimes do things in analog, sometimes in digital, and you may go back and forth multiple times. The question is really about optimality, not so much about some predefined block separations. And so this is something that I'm not only doing now in the context of these two examples that I'm showing. This has sort of become my general philosophy. I'm looking for innovations within that envelope. And so there's a lot of students in my group that are doing similar work. And so with that last slide, I want to thank you for your attention. I'd be extremely happy to answer any questions you may have.
Thanks a lot, Boris, for the inspiring talk. I think I always learn a lot from your talk. We already have quite a few questions in the chat. In case you haven't, to the audience, in case you haven't got the chance to type your question, you can either type in now or raise your hand, so I will unmute you so that you can speak your question. So I think the first question, probably he already watched or read your paper, so the question was posted at the very beginning. So the question is, what are the pivotal challenges in the implementation of analog spiking neural network architecture?
Oh, so I have to admit that I do not work on spiking neural networks. This question would be for Kwabena Bowen, who's my colleague in bioengineering. He works on spiking neural networks. I have never become too fond of these because I don't fully understand the potential advantage. The issue is, how do you build them, right? If you were to build them fully analog, as it's presumably done in the brain, even though it's sort of also mixed signal-like in the brain, how would that scale to a large network? And how do you train such a network? What are the algorithms and so on? So I'm trying to benefit from the wind of the whole digital community and reuse these networks and just sprinkle in a little bit of analog. Right, so I'm actually not qualified to answer that question, sorry.
So for those of you, you will know, Boris always give you very good but also honest answer. Yeah. And maybe because the first set of questions is about spiking neural network, we can skip now and move to the next question. So what's the difference between pure analog and digital? Oh, sorry, digital spiking neural model? Which one is best suitable for
Oh,
analog?
I think I have to pass again. So if, yeah, I can just tell you what's going on in the literature, right? So initially there was Carver Mead is the person who started this whole thing with analog spiking neural networks. And many people have followed that path, and they have engineered a lot of these analog neurons, and some of this work looks actually quite promising, and it was done in the 80s and 90s and early 2000s. And I think over time, just people recognize that it doesn't scale as well. And so even the spiking people have gone to digital, right? So Intel has a spiking digital chip. And so I would say most of this move toward digital is for scalability. And it's kind of a similar trend as for computing in general. We used to have analog computers for sure, right? Hundreds of years ago. We had analog computers, but they became digital because the analog noise accumulation and all this became unmanageable. I mean, this is just a very big picture answer, but again, I am really not an expert in spiking networks.
Oh, thank you. The next one is about your work with Daniel. So the question is, how is the activation function implemented? And does it support all three common activations?
Can you repeat the second part? I didn't get the second part.
The first one is how is the activation function? I guess he or she is asking about the nonlinear activation function. How is that implemented, and does it support all the three common activation? I'm not sure.
Oh, I see. Okay. Yeah, no, we don't. So this is a binary net, and the activation function is really just a slicer. It's a simple threshold activation function. And so we do not support any other activation functions. You're probably thinking about ReLU and hyperbolic tangents and so on. So none of this is in this chip. Keep in mind that we have only 8-bit, single-bit activations coming out here that come back in as input activation. So everything is single bit in this network. So the activation functions are just comparators, and in this design, there was no effort made for other activations. I have to say, in general, right, the community has kind of converged to ReLU activations, which is basically just clipping. It's a very simple activation. So if you had an A to D converter here, maybe I should go to this slide. If you wanted to build an activation function here, after the ADC, you just clip at 0, right? So that would be your activation function.
Thank you. I think the next one is from Samira. So the question is, considering analog nonlinearities and sensitivity to PVT variations in the scale process nodes, how easy it is to get an accurate decision for inference machine learning algorithm in silicon?
Well, I mean, we did this design in 28 nanometers, right? And we actually benefited from the process technology with this approach, because when you look at this, it is actually the most digital analog approach that you could do, right? So first of all, the multiplication is really done with logic gates. And then it's only this charge summation that is analog. And it turns out that these unit capacitors, which we make very small, maybe half femtofarad or so, they match extremely well. The newer the process, the better they match, because the lithography keeps moving. And so this architecture actually scales. And in fact, people are now doing this at 7 nanometers in various companies, and they're exploiting the technology. Now, the more difficult part, if you were to pursue this architecture, is kind of fitting the ADC and the pitch and getting the noise specs on the ADC. This is the more challenging problem and how to do that with low supply voltage. But there, keep in mind that people are solving this on a daily basis. We're building A to D converters in 5 nanometer processes right now as we speak. So this is really the most challenging piece, and that's automatically being addressed. And this piece is not critical at all for PVT. Yeah.
Thank you. And the next one, I think, is from Patrick from Arena. So he's asking, with respect to mixed signal implementation of neural network, I guess the question is for the first work you mentioned, the work with Chris. The data from the sensor is not usually assumed to be raw, meaning there are some form of signal processing, digital in most cases, performed between the sensor output and the neural network input. So would this overhead always limit the performance of a solution when it goes from raw data to the inference?
Yeah, that's a really good point. Well, I mean, in our case, we have images coming in, and yeah, if you need to do some conversion on these images, that can be extremely power hungry. But I mean, in a separate work, right? Last year, we have shown how to do feature extraction out of raw images and so on. So this pipeline before the neural network is exactly the same issue. And the question is very good, because in the end, this may dominate everything. In fact, I have seen some applications where just the input buffer that caches all the data that goes into the neural network is one of the biggest power consumers. So that has to be worked on as well. And there are people looking at event-driven schemes to eliminate this issue. There's, of course, other technology plays, maybe coming up with better memory, maybe compression techniques and so on. But this is definitely true, and this should be highlighted, that when you improve one component in the system, then some other component will sting you really hard. And that's actually happening as we speak. It's a very good question. Yeah.
Thank you. The next one is from my colleague, Kayan Yang. I will let him speak up. Kayan, you are now allowed to talk.
Oh, hi. Can you hear me?
Yes.
Oh, hi, Boris. Thanks for your great talk. I have 2 questions. So the first one is about the neural recording compression. You mentioned that simple thresholding does not work.
Yeah.
But from the results, it seems that if you have a thresholding with hysteresis, it should do the same, right? It can skip the samples in around the baseline and can still keep the spike shape.
But how would you do that?
I can have a Schmidt trigger that has defined 2 thresholds, and then once it go down, I will use the lower threshold. When it go up,
yeah, this is true if I just paint this picture like this. But how would you do it in hardware? It would basically mean that you still have to have the A to D converter somehow available in each pixel, right? In addition to this Schmidt trigger. So you have a multiplexing problem. I guess what I didn't mention is that this scheme not only handles compression, it also automatically multiplexes the data out of the array.
Yeah, that's true. That's a very clever way of.
And so I think your scheme would solve the first problem, but I don't know how I would go about the other one, because I don't know how to multiplex things out then.
I see. Yeah, thank you.
Yep.
And then my second question is, there have been some studies showing that the larger and more complex, because of the low SNR you have for RAM-based memory computing, the mixed signal peripherals will occupy most of the area.
Yeah.
It will diminish the area benefits of RAM cells compared to, say, SRAM.
Yeah.
So I want to hear your opinion on this.
Yeah, this is definitely true. This is a huge issue. And my answer is we need to become a little more creative. I mean, what we've seen so far is still relatively simple. We had a paper at the end of last year where we basically tried to use the RM cells themselves to build part of the data converter. So what we did is we used a certain number of rows to build a DAC, and this DAC is trying to null the bit lines successively. And so now you actually have a very dense DAC integrated in the array itself at the right pitch, and then you only need a comparator at the periphery anymore. And so ideas like this, I think, will be key to making this work. I think pushing, high fidelity ADCs into the periphery of these RMs that are built with vanilla devices and capacitors and so on is going to be very difficult to fit. So basically, I would say, this is not a solved problem. We need to work on it, but I think there's ideas on the table.
Yeah, thank you. Thank you very much.
Yeah.
Thank you. Boris, do you have a few more minutes? There are still quite a few questions.
Yeah, I have nothing to do. It's COVID-19, so.
Great, thank you. The next question is about slide 42. So the number of bits is for weights or for the signal?
Both. It's for weights and input activations. I kept the number the same, but you could come up with different combinations. I just kept it simple here.
By the way, I got inspired by this figure. So a few years back, I think the Sonic E symposium, the very first one, you taught to me how to start from the thermal noise to think about this aspect. Thank you. I think the audience learned similar aspect as well. So next, Chao Jian, would you like to speak your questions?
Hello, Professor Murmann, can you hear me?
Yeah.
Okay, thank you. So my question is that I noticed that in your mixed signal BN chip, you add some expert knowledge to the model structure. For example, I remember all the layers have the same input and output channels. So my question is that do we have any method to quantify the energy overhead of irregular models before typing out? Because I noticed the model you use is quite regular.
Yeah.
Or in other words, do we have a general rules for the model design in such a mixed signal chip?
Yeah, well, I mean, for the mixed signal chip, we would like it to be regular like this, and that's why we did it this way. Of course, this is not necessarily good for the algorithm, and there may be overhead associated with it. But this is what we did at the time, and I already told you using 2x2 filters was not a good idea. We should have done 3x3. But this is precisely what I meant at the end by future work. I am unaware of an environment that basically takes the mixed signal trade-offs and maybe energy numbers and various costs and benchmarks, and basically invents the right neural network topology. They are developed by different metrics now, right? For example, whoever did MobileNet, they just try to minimize, say, the number of parameters. But maybe that's not the right metric, right? So it's just a good guess that fewer parameters is good. But there may exist networks that have more parameters, but a structure that is more amenable for mixed signal acceleration. But we haven't discovered these because no one has ever worked on it. So I think this is actually a very, very good question, and it deserves more research that Yingyan and I want to work on together. So maybe you can join the fun.
He's one of my students, so we discussed this in the group. Yeah.
Okay, thank you, Professor.
Yeah, I wish I knew. I really wish I knew.
So Hao Rang, would you like to speak your question? Next is you.
Yes, sure. Hi, Professor. My question is quite general. So is there a guaranteed optimal customized memory or circuit architecture for deploying a given network, like VCC nights? Or in other words, is there a bound to indicate how efficient we can achieve given the network and the hardware resources?
This is a tough question. I mean, I can give you bounds for very simple things, you know, like what I have done in the past to get motivated to working on this even is when you look at digital accelerators and you look at the cost of a multiplication and maybe 3 register file accesses, you very quickly end up with maybe 100 femtojoule or so. And in this case, it's very clear that you cannot get a better overall compute efficiency of 10 tops per watt, right?
Yeah.
Along similar lines, it's very difficult to imagine that even with an array like this, where everything gets amortized really well, and you will still have some switched capacitance and there's relatively low activity factors. When I multiply all of this together, it's actually very difficult to see how you could possibly get better than, say, one pops per watt, so 1 femtojoule. One femtojoule per op, and this is kind of where these curves terminate roughly. You see this? This is about 1 femtojoule per Mac, or 2 femtojoule per Mac, 1 femtojoule per op. Because this is not limited by thermal noise, this is just a little bit of switching activity per operation. It's very difficult to get better. There are some folks at IMEC who say they can get 10 pops per watt with some emerging technology that is very dense. But I think this is an array level metric that is not necessarily, this won't hold up at the accelerator level when you account for data movement and things like that.
Okay, thanks.
Yeah.
And for the next question, so the ID is called Yunuts. So I think I unmuted you. Could you speak your questions? Okay, if not, maybe I will speak up the question. These issues, we alter the mismatch in caps in the mixed mode synapse. I see there was a differential design of it.
Well, we did the differential design mainly to suppress any kind of coupling noise. So when you have digital signal switching and coupling into these charge collection wires, we wanted to suppress this because if you have differential signals, it becomes a common mode, right? That was the main reason, and we were scared because we did this for the first time. Meanwhile, people have done single-ended designs that work perfectly fine. So I think it's okay if you know what you're doing. It's actually possible to do this in a single-ended way, I believe. So we just played it safe here. This is not necessarily a template for the future, I would say.
Thank you, Boris. Sorry to keep you long. Maybe we will allow the last 2 questions.
Okay.
So Jay Hang, I unmute you. Can you speak up your question?
Yes, thank you, Professor Boris, for the talk. My question is more towards the RF application side. When you discussed about ADCs and their reduction in energy in this design, I don't. Will it still work when we go towards higher frequencies?
Oh, yeah. So let me make some disclaimers about this plot that I showed. You are probably referring to where is it? This plot, right?
Yes, sir.
So this plot is actually mainly for low frequency. So what I did here is I picked the most efficient ADCs in each year, and those are not high frequency ADCs. So for high frequency, for the ultra high frequency ADCs, you actually have some very nasty proportionality to frequency squared and so on. And they tend to be up to, I mean, at least an order of magnitude worse than this or more. And so these ADCs are still technology limited. And so hence they can actually still improve, but they are inefficient to begin with. You know what I mean? So
yes.
So here I'm mostly focused about sensor type applications, imaging and so on, something that works below 100 megahertz, maybe that would fall on this chart. Once you go into the gigahertz, everything is quite different.
Thank you, sir.
Mm-hmm.
I'm gonna take the last question. So, Boris, I really like the slides you showed twice. The insights you taught us. For example, from the first one, you innovate the processing pipeline, and then also later you share how to increase the computation density to amortize the memory access and the interfacing costs. And also later you talk about the flexibility, increase the flexibility, maintain the efficiency. Also your work with your student like the Bina, and the one with Daniel. And said, I think still maintain the most efficient design in the community. So where, in addition to those where should we look for the next one order or more efficiency gain? This is more, would like to hear about your visionary thoughts.
Yeah, this is an extremely good question. I think it relates a little bit to what was said earlier. If you really wanted to squeeze this even further, we have to start engaging in circuit and architecture co-design, more or less what we're talking about, because this network architecture that we have here in itself is actually quite inefficient. First of all, binary net is not very efficient to start with, right? It needs a very high dimensionality to resolve this very simple problem. So going to a couple of bits would simplify this. The layers and layer types are probably not optimal because we just do vanilla convolutions here. Probably we could do some interesting bottleneck layers, and if we have good implementations of these in mixed signal, that would give us a lot of efficiency. So when you ask for a factor of 10, I think it's really like 3 factors of 2, and they come at different, abstraction levels. We will get better at the circuits. We will get better at the DNN architecture, at the frameworks, and we will continue to scale the technology and maybe bring emerging devices in there. But yeah, that's basically what it is. So you need to take kind of the nth root of 10 and distribute it out across the stack. I don't think there's one little thing that can save you.
Thank you. I think this is also an encouraging answer. So I know there are some undergraduate students here. They would not like be dragged by the overwhelming news for the algorithm level. So you mentioned the device and the circuits.
Yeah.
Thanks a lot. Thank you so much, Boris, for the stellar talk. Really, I think this is the crowded talk during this summer I have attended. And also, thanks a lot for spending this time with us. So also thank you all very much for attending the talk and ask those questions to engage in the talk. Thank you, Boris. I'll see you.
Thanks, everyone. I'll see you again in better times.
Yeah, I see you this Thursday.
Right.
Thank you. Thank you very much all.